Here we're looking at calculating the enthalpy of a reaction based on a practical that was done in the classroom using copper sulphate and iron. The practical involved adding 0.558 grams of iron to 25 centimetres cubed of copper sulphate and looking at the temperature rise over time. Now, in calculating the enthalpy of a reaction, a lot of you got confused as to which numbers you needed to use in calculation of numbers of moles. A couple of reasons for this are you're not yet familiar with looking at which reactant is limiting and which reactant is in excess, and also using the question to indicate exactly what you're looking for. So the question was to calculate the energy per mole for iron specifically. Whenever I start with any calculation, I always put the equation out first, followed by the stoichiometry, and then the indication underneath as to the information that I've already got. So here we've got the concentration of copper sulphate, the volume that we used, and then we have the mass of iron that we used. Now I would start just by looking at calculating how many moles of iron are used. This is different sometimes to the amount that were added, depending on whether the iron that's added is in excess or whether it is the limiting reactant. So it's prudent to find out how much iron and how much copper sulphate you have. So using the two calculations, N equals CV for the copper sulphate and N equals M over M for the iron, I've worked out here that the number of moles of copper sulphate is 0.025 and the number of moles of iron is 0.01. Now this means that the copper sulphate is in excess and iron is the limiting reactant. So when the reaction has finished, we can be certain that we have used 0.01 moles of iron. That means that when we do our calculations for our energy released, we know that the energy released has been per 0.01 moles of iron, not for the copper sulphate. Because actually, even though we've got 0.025 moles of copper sulphate present, because of our stoichiometry, when the reaction has gone to completion, we will still have used exactly the same number of moles of iron, so 0.01, as we have the copper sulphate. Taking it across, in order to do our calculations, we need to use the equation Q equals mc delta T. The M is the mass of the fluid. This is the mass of the water or the aqueous solution. So in this particular example, it's the volume and therefore mass of the copper sulphate. The reason that we use 25 is we assume that aqueous solutions have the same density as water. Therefore, we equate 1 centimetre cubed to 1 gram. So we've got 25 centimetres cubed, 25 grams of the liquid. This is not the mass of the iron, it is not the mass of anything else. It has to come from the liquid that you're using. We've then got C 4.81, which is our specific heat capacity of water, and again, as I mentioned, we assume similarity and parity between the aqueous solutions and water. And then we've got delta T, which is 4. Your value may be different from mine, but I saw a temperature change of 4. Your values following this, therefore, may be slightly different to mine, so it's the method that's important rather than the numbers. If I do this sum, what I end up with is 418. This is in joules. To get it into kilojoules, I need to divide through by 1,000, which gives me 0.418 kilojoules. And this is a number of kilojoules that were released for the number of moles of iron that we used. And we calculated earlier that this is 0.01. From the question, it asks us to calculate the enthalpy change per mole of iron, not per mole of copper sulphate, but per mole of iron. So when we're looking at it, we need to take our energy change, our enthalpy change, and divide through by the number of moles that we've used. So we take in kilojoules, the value that we calculated, we take our number of moles, 0.01, from what we calculated earlier on for the moles of iron, and if we take that through, we end up with 41.8 kilojoules per mole. So mole minus 1 is the per. Now this here represents the number that is important, but in addition to the number, the sign is also significant. So as delta T was an increase, the reaction is therefore exothermic. And because we've got an exothermic reaction, we know that exothermic reactions have a negative sign, and therefore our delta H is going to be minus 41.8 kilojoules per mole.